Welcome back everyone to part 4 of our 5-part video series about the Trinity demonstrator at the Fraunhofer IWU. This video will focus on the handling and assembly module. You will learn about its concept, its benefits, and how to use it. The process to automate a manual workstation is not always completely clear or straightforward. In order to transform the existing manual workstation into our automated demonstrator, a certain planning process was followed. This planning process includes certain aspects that have to be considered and questions you have to ask yourself in order to successfully automate a manual workstation. These questions include how to organize the process, what steps to follow, which preconditions are to be considered. The training is structured in the following parts: application and benefits, requirements, the planning flowchart we developed, and conclusion and next steps. Let's start with the related use case, its application and benefits. Due to the demonstrator's nature of being a low-cost automation solution, the solution targets small and medium enterprises, since full automation solutions require an investment that is multiple times higher. The handling and assembly tasks of the demonstrator are of importance for the industrial sector and especially for the electronic and mechanical engineering sector. Since handling and assembly tasks have a wide range of applications, different fields of use are also possible. The module is in so far connected to the use case that we use the module's phases during the development of the demonstrator. The more complex the workstation, the higher is the amount of interdependencies that have to be considered during planning. The module supports considering the most relevant aspects, thus increasing the chance of identifying planning errors during early phases of development. The module provides new input that is supposed to support planning engineers in streamlining the planning process. Since the use case is industry-related and not purely academic, some aspects might apply to your own processes. The most important benefit is that corrections during the planning phase cost only a fraction of the cost of changes during later production phases. Next up are the module's requirements. To use this module, no specific knowledge is required. However, it is recommended to watch the previous parts of the video series to get detailed information about the structure of the demonstrator. If you want to operate a workstation similar to this demonstrator, robot programming skills are necessary. And for the transition from a manual workstation to an automated one, a MTM analysis is needed to identify the process times. A couple of technical requirements are necessary for the demonstrator. An industrial robot with adequate specifications regarding its reach, payload, and accuracy is needed. Further needed equipment are a robot controller, a PC for offline programming, a suited handling tool, safety equipment, and a vision system with image recognition software. This concludes the preliminary information about this module and leads us to the content of the handling and assembly module itself. To streamline your planning process, we developed a planning flowchart which is supposed to support you during the development phase of automating a manual workstation. Our demonstrator was developed following the steps I'm going to present you. The complete flowchart is uploaded to the Trinity online training platform. Following the flowchart, we reduce the amount of overlooked planning aspects. We will now take a look at the planning flowchart. The first step is working through the inputs that might act as boundary conditions for the workstation. Having a precise understanding about the existing conditions and restraints for the workstation might make some decisions during the planning process obsolete. To name just a few possible inputs, important factors might be available budget and workspace, logistic requirements, and condition of the components. In the second step, the workstation's tasks need to be defined, since the necessary equipment can directly be derived from the task. As an example, additional inline quality control will require measuring systems. Afterwards, the desired degree of automation is determined. In our demonstrator, about 50% of the work content is automated. As soon as the degree of automation is known, the process can be divided into tasks for humans and for the technical system, I will explain next how MTM analysis can support this division. The previous video gave an insight on how to measure process times using MTM analysis. We performed the MTM analysis at the existing workstation in order to divide the process tasks between human and machine. In the first step, we analyzed the existing assembly steps. Then, we measured the process times of the assembly of each component. This allows us to allocate the components on two workstations while taking into account that the process times at both workplaces should be equal to avoid standby time. After looking at the process times, a third step is performed, in which the geometry of the components comes into play as well. If the component's geometry is too complex for a technical system to handle, it should still be assembled by a human. Considering the geometry will lead to some adaptations of the allocation, but all in all, the even distribution of process times must stay in balance. The result of the allocation on two workstations is displayed on the right. The components on the upper printed circuit board are assembled by a human, whereas the components on the lower printed circuit boards are assembled by a technical system. Let's continue with our flowchart. The next step is the definition of the material flow into and out of the workstation. Considerations about material placement, intermediate storages, and transportation media are made at this point. Next up is the allocation of system tasks. System tasks such as handling, quality control, or assembly are defined and are distributed to the according handling tools, sensor technology, and additional devices, for instance repositioning fixtures or forming devices. Then, the maximum cycling time should be estimated or determined if possible. Afterwards, the necessary degree of freedom for the handling tools has to be determined. This step is important for the technical system that is going to be chosen in a later step, since some systems might not be suited due to the required degrees of freedom. In the next step, it has to be considered whether the provision of the components needs change due to desired velocities of the process or due to reach constraints. If yes, the provision of the components has to be changed and the process leads back to the allocation of system tasks. Adaptations can be done by providing component containers in different sizes or changing the arrangement. If no changes are required, the process continues with the creation of a rough layout. This layout should consider worker pathways. If the rough layout is made, the minimum speed in which the handling unit must operate should be determined to reach the cycle time. The next step is the design of the gripping unit, which includes a couple of steps to guarantee that the correct gripper is developed. The gripper needs to be adapted to the specific gripping task it has to perform. Therefore, the operating principle must be chosen. Operating principles are form and force fit, magnetic or suction. The correct selection of the principle depends on the size and material of the component. Next, specific specifications such as safety aspects and requirements for a certain accuracy have to be considered. This concludes the considerations for the gripper, and the actual design process of the gripper can be conducted. After designing a suited gripper, the total load has to be calculated. The total load consists out of the gripper plus the component it has to hold. Having performed all the mentioned steps, it is now the time to select the type of technical system or robot that is going to perform the handling operation. Possible technical systems are a SCARA robot, an industrial robot, parallel cinematics, linear axis, or rotation axis. The considerations from the previous process step influence this decision. The degree of freedom, the process task, the special specifications, the total load, and the speed requirement all have to be considered when selecting the most suited technical system for your application. This leads us to the last couple of steps of the planning flowchart. At this point, the kind of technical system is selected. Therefore, additional specifications that are necessary have to be considered. Specifications that require additional care could be clean room applications, resistance against splash water, close interaction between human and robot, or even protection from explosions. If any of those categories apply, you must take adequate measures. Next up is the dimension of the system or the selection of a specific robot model. This highly depends on the necessary payload, the required reach, the mounting position of the robot, and available media connections. This leads to the determination of additional required peripherals. The list of possible peripherals is long and highly depends on your applications. Possible peripherals are, for instance, input-output device, human-machine interfaces, hydraulic power units, compressed air generators, or valve clusters. After considering the peripherals, you should select the safety equipment. Depending on the application, partition walls, safety doors, or separating grids might be necessary, or other safety equipment such as light grids might be sufficient. With the necessary safety equipment determined, the total needed space for the workstation can be calculated. Since the workstation's layout is now determined, it is possible to fully determine the safety concept, the mechanical design, and the necessary control technology. The final step, planning the vision system, will not be discussed now, but rather in the next and last video of our video series. Thus, we made it through the complete flowchart. The flowchart is supposed to guide you during your process of automating a manual workstation. It resembles the process steps we performed during the development process of our Agile manufacturing demonstrator. This video explained in detail how the developed flowchart for planning the automation of a manual workstation can be used and what its advantages are. The next and final video will contain information about the process of implementing a vision system. This wraps up our fourth video. See you in the next and last video of our video series about our Trinity demonstrator for Agile production.